Welcome to G Fun Facts Online. Today, we're venturing to the frontiers of chemistry to talk about a class of molecules we could call superalcohols. These aren't your everyday ethanol or rubbing alcohol. These are molecules that push the very limits of what scientists thought was possible to create, from substances forged in the cold of deep space to intricate molecular fortresses built in the lab. It's a story of creativity, perseverance, and the relentless pursuit of molecular mastery. Let's start with a molecule that was, for over a century, a ghost in the machine of organic chemistry. Its name is methanetetrol. Imagine a single carbon atom. Now, imagine trying to attach 4 hydroxyl, or OH, groups to it. For decades, the rules of chemistry said this was impossible. The general principle is that a single carbon atom just can't tolerate being bonded to more than one hydroxyl group. The oxygen atoms are highly electronegative, and packing 4 of them around one carbon creates immense strain, causing the molecule to instantly fall apart. It was predicted to be far too unstable to ever exist. Yet, in mid-2025, scientists announced they had done the impossible. They synthesized and detected this elusive superalcohol. But they didn't do it in a normal laboratory flask. To create this impossible molecule, they had to recreate the brutal conditions of an interstellar molecular cloud, the frigid near-vacuum nurseries where stars and planets are born. Researchers at the University of Hawaii at Manoa took a mixture of simple, common molecules you'd find in space, water and carbon dioxide, and froze them onto a surface at a mind-bogglingly cold 5 Kelvin. That's minus 268 degrees Celsius, just a few degrees above absolute zero. This created an icy film, like the frost on a cosmic dust grain. Next, they bombarded this ultra-cold ice with high-energy electrons, simulating the effect of galactic cosmic rays that constantly zip through space and trigger chemical reactions. As they gently warmed the ice, the newly formed molecules were released as a gas. Using a powerful detection technique involving mass spectrometry, they found it, the fleeting signature of methanetetrol. While it is incredibly unstable, the extreme cold and isolation of the experiment gave it just enough time to exist and be detected. This discovery is more than just a chemical party trick. It has profound implications for the origin of life. Scientists describe methanetetrol as a prebiotic bomb, or a seed of life molecule, LOC. Its instability is exactly what makes it so interesting. When methanetetrol gets a jolt of energy, it decomposes, but in doing so, it releases a cocktail of life-relevant compounds. It could act as a chemical trigger in the cold, dark expanse of space, providing the raw materials for more complex organic molecules, the very building blocks of life. This discovery gives huge weight to the idea that the precursors to life may have formed in space and were delivered to Earth on comets and asteroids. Now, while methanetetrol is a fascinating extreme, chemists on Earth face a more practical but equally daunting challenge: building sterically hindered alcohols. Picture a molecule where the important hydroxyl group is surrounded by large, bulky chemical groups, like a VIP surrounded by bodyguards. This molecular architecture is incredibly valuable. In pharmaceuticals, for example, this steric shield can protect a drug from being broken down by enzymes in the body, making it more effective. But building these molecular fortresses is tough. Chemical reactions depend on molecules approaching each other in just the right way. When bulky groups get in the way, they block this approach, and the reaction fails. For over 100 years, the champion tool for this job has been the Grignard reaction. It uses a magnesium-based reagent to attack a carbonyl group, like the one in a ketone, to form a new carbon-carbon bond and create an alcohol. You can even do this iteratively. Take an alcohol, oxidize it to a ketone, add another group with a Grignard reaction to make a more complex alcohol, and repeat. It's a powerful way to build complexity step by step. But even the mighty Grignard reaction has its limits. If both the ketone and the Grignard reagent are exceptionally bulky, the reaction can fail. The reagent might not be able to reach its target. This is where modern chemistry gets even more creative. A huge goal isn't just to build these complex molecules, but to build a specific version of them. Many complex molecules are chiral, meaning they exist in two mirror image forms, like your left and right hands. In medicine, this is critical. Often, only one hand is therapeutically active, while the other might be useless or even harmful. Creating just one specific version is called asymmetric synthesis. Chemists achieve this by using special tools called chiral ligands, which create a chiral pocket around the reaction, guiding the molecules to connect in a way that overwhelmingly favors one mirror image product over the other. As the demand for more complex molecular architectures grows, chemists are developing even more advanced strategies. One incredible method uses light to drive a reaction. It's called photoredox catalysis. This technique can generate two different highly reactive species called radicals at the same time. These radicals then find each other and couple together, forging a new bond in a very crowded environment where traditional methods would fail. It's an elegant way to install a bulky group under very mild conditions. Another cutting-edge approach uses a special class of organic catalysts called N-heterocyclic carbenes, or NHCs. In an innovative process, an NHC is used to trigger a cascade of events where a molecule breaks apart into a pair of radicals that are held closely together and then almost instantly recombines in a new, highly complex arrangement. This allows for the rapid construction of incredibly congested alcohol structures that were previously very difficult to make. And then there's biocatalysis, using nature's own master chemists, enzymes. Enzymes build the complex molecules of life with flawless precision. Scientists are now harnessing this power in the lab. Enzymes like ketoreductases can perform reductions of ketones to produce specific chiral alcohols with a level of selectivity that is hard to match with traditional chemicals. And they do it in water under mild conditions, making it a very green approach. Through a process called directed evolution, scientists can even mutate and evolve these enzymes to perform new, non-natural reactions, tailoring them for specific, super-hindered targets. Moving on from building complexity around a single point, there's another fascinating way to create superalcohols, by making them bigger. This is the world of the Guerbet reaction, a process that takes simple primary alcohols and essentially fuses them together to create larger, branched-chain alcohols, with roughly double the molecular weight. The products called Guerbet alcohols have a unique branched structure. This branching disrupts how the molecules pack together, giving them extremely low melting points and making them excellent lubricants, surfactants, and ingredients in cosmetics. The Guerbet reaction is a beautiful example of a domino process, where a series of reactions happen one after another in a single pot. It all starts with a catalyst that does two jobs. First, it pulls hydrogen off the starting alcohol to form an aldehyde. Then, with the help of a base, two of these aldehyde molecules react and join together. Finally, the catalyst uses the hydrogen it borrowed in the first step to convert this new, larger molecule back into the final branched alcohol product. It's an elegant cycle where the starting material itself provides the hydrogen needed for the final step. Traditionally, this reaction required harsh conditions, high temperatures, and pressures. But modern research has developed advanced catalysts, often using metals like ruthenium and iridium, that allow the reaction to run much more efficiently at lower temperatures. This is especially important today, as we look to upgrade renewable alcohols from biomass, like bioethanol, into advanced biofuels like biobutanol. The Guerbet reaction is a key technology for making this happen. For a century, this reaction could only produce a random mix of mirror image products. But in a recent landmark achievement, chemists developed the first asymmetric Guerbet reaction. Using a chiral catalyst, They can now couple two different alcohols together to create a new, specific chiral alcohol with near-perfect selectivity. This transforms the Guerbet reaction from a bulk chemical process into a sophisticated tool for making valuable, complex molecules. All of these advanced techniques for making superalcohols stand on the shoulders of fundamental reactions you learn in introductory chemistry. The addition of water to alkenes, the reduction of carbonyls with reagents like sodium borohydride, and the substitution of alkyl halides are the foundational building blocks. Chemists assemble these basic moves into complex, multi-step sequences to create the advanced starting materials needed for these frontier syntheses. The quest for superalcohols is not just about making cool, complex molecules. It's about pioneering greener and more sustainable chemistry. The future is being defined by a focus on atom economy, making sure every atom from your starting materials ends up in the final product, as well as asymmetry and automation. We are seeing a major shift away from fossil fuels toward renewable feedstocks. Alcohols can now be made from biomass or even from captured carbon dioxide. These green alcohols can then be used in reactions like the Guerbet condensation to create valuable chemicals in a circular carbon economy. Innovations in catalysis are also changing the game. Using light-to-power reactions, harnessing the precision of enzymes, and integrating different types of catalysis into one-pot cascades are all making synthesis more efficient and less wasteful. The very way we do chemistry is changing, moving from single flasks to automated continuous flow reactors that offer better control, safety, and scalability. From the cosmic chill, where an impossible molecule is born, to the intricate dance of atoms in a perfectly controlled asymmetric reaction, the synthesis of superalcohols embodies the spirit of chemical exploration. It pushes the boundaries of stability, complexity, and selectivity, and in doing so, it unlocks new functions, new materials, and a deeper understanding of our chemical world. The next generation of superalcohols will undoubtedly lead to scientific breakthroughs and technological innovations we are only just beginning to imagine.